Okay, another area mentioned was expressions, mathematical expressions.
Yes, stacks are super useful here for several tasks. One big one is checking for balanced parentheses.
Making sure all the opening brackets have matching closing brackets. Like a plus bc is okay, but a plus bc is not.
Exactly. Or which is balanced versus which isn't nested correctly.
How does a stack help check this?
It's a neat algorithm. You scan the expression. When you see an opening bracket, like, ah, or no, you push it onto the stack.
Okay, remember the opener.
When you see a closing bracket,
Yeah.
or you look at the stack, is it empty? If yes, you have a closer with a no opener, so it's invalid.
Makes sense.
If the stack is not empty, you peek at the top element. Is it the matching opener for the closer you just found? Very for
Got match the type.
right. If it is a matching opener, then great. You pop the opener off the stack, effectively canceling out the pair.
Okay, pair found and removed.
If it's not the matching opener, like finding a wood when it is on top,
Yep.
then it's invalid nesting.
Got it. And what about when you reach the end of the expression?
After scanning the whole thing, you check the stack one last time. If the stack is empty, it means every opener found a matching closer and everything was nested correctly. The expression is balanced.
But if the stack is not empty,
That means there were leftover opening brackets that never found their closing match. So the expression is unbalanced.
that's a really clear algorithm. The C++ code snippet seems to follow that logic. It pushes openers and tries to pop matching closers.
Yeah, it iterates through, uses a stack, and checks those conditions. If stk.empty is true when it needs to pop, or if it's not empty at the very end, it flags it as invalid.
The example, a plus bc, de, being invalid, makes sense. It would leave opening parentheses on the stack at the end.
Correct. And the multi-bracket example, a plus b, c plus d plus e, would pass because everything matches up correctly.
Okay, that balancing act is clever. What else with expressions? You mentioned different notations.
Right. We usually write math in infix notation, where the operator is in between the operands, like a plus b.
Standard stuff.
But computers often find it easier to work with postfix or prefix notations. Postfix, also called reverse Polish notation or RPN, puts the operator after the operands. AB plus.
AB plus instead of A plus B.
Okay.
And prefix.
Prefix puts it before plus AB.
Why use these other notations? Postfix sounds particularly interesting. The notes say no precedence, rules, or parentheses. No precedence, rules, or parentheses needed.
That's the big win for postfix. When evaluating a postfix expression, you just scan left to right. You push operands onto a stack. When you hit an operator,
Let me guess. You pop the operands you need, do the operation, and push the result back onto the stack.
exactly. If it's a binary operator like plus and in, you pop two operands, calculate the sum, and push the result. The order is entirely determined by the sequence. No need to remember that multiplication comes before addition or worry about parentheses.
So 3, 5 plus 2 would be.
Push 3, push 5, C plus 5, pop 3, calculate 3 plus 5, push 8, then push 2. Then C in, pop 2, pop 8, calculate 82, 16, push 16, final result is 16.
Which is the same as infix, 3 plus 5, 2. Okay, I see how that works. The example 355 plus 2, 2 looks complicated though.
Let's trace it quickly with a stack.
Okay.
3 minus push 3 stack. 3 pop 5, plus 1 5 stack. 3 5 5 5 minus push 5 stack. 3 5 5 minus pop 5 pop 5 5 5 1 push 1 stack. 3 1 minus pop 1 pop 3 pop 1 pop 3 push 3 stack. 3 5. Wait, I think I misread the previous operation. Let's retrace. The previous operands were 5 and 1. Let's correct that. Okay. After 5 5 1 stack is 3 1. Now we see it. Pop 1 pop 3. Calculate 3 1 push 3 stack 3. Let me look at the slide again. The slide example calculation is different from my quick trace. Let's follow the slide's logic for 3 5 5 plus 2 time middle.
And following the provided trace.
Push 3, push 5, stack. 3 5 5. C, pop 5, pop 5. Calc 55 plus 1. Push 1, stack. 3 1. C, pop 1, pop 3. Calc 31 equals 3. Push 3, stack. 3, C plus 5. This seems wrong compared to the slide example. Let me reread the slide example's infix equivalent. 3 plus 5, 5 5, 2 2. Okay, the evaluation needs to follow that. Let's trace the postfix 3 5 5 plus 2 2, matching that logic.
Right, matching 3 plus 5, 5, 2, 6.
Okay, push 3, stack. 3 push 5, stack. 3 5, push 5, stack. 3 5 5. Operator 5. Pop 5, pop 5. Calc 5, pop 5. Calc 5 5, next 5. Push 1, stack. 3 5 1. Operator. Pop 1, pop 5. Calc 5 1, pop 5. Push 5. 3 5. Operator plus guy. Pop 5, pop 3. Calc 3 plus 5. push 8, stack 8, push 2, stack 8, 2, push 2, stack 8, 4, operator matter 2, pop 2, pop 2, calculate 2, result, push 4, stack 8, 4, operator pop 4, pop 4, push 4, end of expression, result is 4.
Ah, okay. That matches the infix result and makes sense. So the stack keeps the intermediate operands ready.
Exactly. And it's evaluated strictly left to right using that stack mechanism. Very efficient for a computer.
And converting from our normal infix to this postfix form, that example A plus B, C, D, E, F plus G, conversion looks non-trivial.
It involves another algorithm, also typically using a stack, this time to handle the operators and respect precedence rules and parentheses during the conversion itself. Operands usually go straight to the output, while operators get pushed onto the stack or popped to the output based on precedence. It ensures the resulting postfix sequence maintains the original infix meaning.
So stacks help convert to postfix and then evaluate postfix.
Correct. And the advantages are clear. Single stand evaluation, no need for parentheses in the postfix form itself, which means efficiency.
Makes sense why it's used in things like compilers or certain calculators then. That infix versus postfix slide is a good prompt for thinking more about it.
Definitely. It highlights how changing the representation using tools like stacks can simplify computation.
Okay, so let's try and wrap this up. We've covered a lot in this deep dive on stacks.
We really have. From the basic idea and LIFO
Last in, first out.
to the core push and pop operations and the helpful ones like top, size is empty is full.
We looked at how to use them for reversing sequences, which was neat, and how they're implemented using arrays as an example, including the pitfalls like overflow and underflow.
And those crucial error checks needed in the code.
Then we dove into the really important applications. Backtracking for problem solving like mazes.
And the absolutely fundamental role they play in managing function calls via the call stack and activation records in pretty much all programming.
Plus, their use in handling expressions, balancing brackets, and enabling efficient postfix evaluation.
It really shows how this relatively simple data structure is a power behind the scenes.
It's a fundamental building block underpinning so much technology we use without even thinking about it, like the back button or undo.
Absolutely. Understanding stacks gives you real insight into how computers manage processes and data.
So for a final thought to leave our listeners with, maybe think about where else that LIFO principle pops up in everyday life. Beyond books or plates, are there other stacks controlling processes around us?
That's a great question. And maybe also consider that postfix idea, if you could train yourself to think in postfix, could you do calculations faster without needing parentheses? How does structuring the problem differently change how we solve it?
Interesting things to ponder. It really shows how these core computer science concepts connect to broader ideas about process and problem solving. Thanks for joining us on this deep dive.